let's go over some of the theory behind pure bending, and in this we'll delve a bit deeper in than we did last year. So just a quick recap, of course. So bending, you got a moment applied to either end. If that's all you're doing, then you got a pure bending moment. No shear load. It'll be constant throughout. If you want to resist this, then what you need is the normal stresses across the cross section must be, when you integrate those normal the local stresses that arise across the cross section, then the net result needs to be that bending moment. And when I say net result, I mean it needs to be just that bending moment. No axial forces arising as a result, and no shear going on either. So you always end up with some sort of variation in the stress going on. You're always going to have what we call a neutral axis. Essentially, there's going to be kind of a line that you could draw across the cross section that will have zero stress along it. And then the stresses increase and decrease as you get away from that. So the further away from that line, you're either going to have more positive stress or more negative stress, more compression or more tension. So we know that we're operating. We're assuming we're operating within elastic limits, so that stress is proportional to the strain. And that's why we get that linear increase away from the neutral axis, because essentially there's kind of you can kind of think of about that neutral axis as a pivot point. Everything's kind of pivoting around that, so the parts of the cross section that are furthest away from that get stretched the most as you try to pry that apart, and then on the other end as you try to push it together for the negative portions. So we got that bending moment. We know that that bending moment needs to be, the total bending moment that we're applying needs to be equal to the integral of all these little bits of forces times their distance away from that neutral axis. And here we're making the assumption that so we get a neutral axis. Neutral axis will always pass through the centroid of the cross section. In any instance, this formula here is relying upon the notion that we're working with one of the prime axes, one of the primary axes. So basically, we're looking at it at an orientation where the I is either at its maximum or at its minimum. And that's what allows. Yeah, well, I'll get to that in a second. But anyways, so we're increasing our distance y here, or we're decreasing it, and then multiplying that by the little bits of force that arise. Those little bits of force arise due to the stress times that area. So we just need to take that and then again, the stress here is, because it increases linearly from the neutral axis, can be thought of as a function of the maximum stress that arises times this ratio here of the distance from the neutral axis to kind of the maximum point. So we got the m is equal to the maximum stress divided by c, so that's just the maximum distance from the neutral axis, times this y squared dA term, this integral of y squared dA term, and that's where we get to use the I being either maximum or minimum to make this substitution here that is equal to I. So our maximum stress is just a function of the moment times the maximum distance from the neutral axis to I, divided by I, and then the moment in general, the stress in general, negative my over I. So the negative sign there, again, that's due to our sign convention. So you'll remember that our sign convention is that if we are bending something so that it's making a smiley face, like this, that's defined as a positive moment. So if we looked at the cross section here, and we got our neutral axis right here, if we want to bend, a straight bar into a shape like that, then what we're going to need to do is we're going to need to make the bottom of that bar longer, and we're going to need to make the top of that bar shorter in order to do that. So essentially, when our y increases, our stress level needs to be becoming negative, and when y decreases, our stress level needs to start to become positive. So we don't always have symmetric bending. We don't always, we're not always going to be applying a bending moment across about an axis that corresponds to one of the axes as the primary axis. So one of the axes about which the I is a maximum or minimum. So if it isn't, then essentially what we need to do is we need to kind of just figure out what it would be for one of them and add it to what it would be for the other, and then we get the combined factor. So here we're applying a moment that is about some axis. Oh, sorry. A moment about some axis that is offset from the this z-axis here by this angle theta. So we've got that angle theta there. So what we could do is we can break this moment up into its components that are parallel to the z-axis here and a component that's parallel to the y-axis here. And essentially, we just use our principal superpositioning here. So if we add up the effects of this moment, which we can calculate using the flexure formula that we just talked about and derived, and this one, which we can use using the same formula, just about a different, it's about a different axis, but it's about an axis that's perpendicular to the principal axis. So that means that axis is the other principal axis. That's the way that works. Or I guess one of the other principal axes, because there are some geometries where you could have more than one principal axis. Like for example, if you have a octagon, well, then you got a principal axis here, you got a principal axis here, but you also got a principal axis here, and you also got a principal axis here. But anyways, that's a bit of an aside. So yeah, we just combine those two effects, and that will give us the stress level at any point on the at any point on the cross section. Now, one thing to keep in mind here is that what we want to be doing is we want to be defining this angle here, this angle theta here. It needs to be relative to one of the principal axes. There's no other. It's only the. It's basically only the principal axes and the relative yeah, it's the principal axes that need to be defining your coordinate system here. So, for example, if you have a weird shape, if you have a cross section that looks like this, then just at a glance, I would say that your principal axes are probably going to be something like this, maybe a bit higher. But if you go ahead and if you're just applying a moment about this axis here, which, you know, for most problems, we probably consider that to be the z-axis. But since that z-axis isn't one of the principal axes, what we need to do is we need to redefine the angle the moment is acting at relative to those principal axes, and then we use that to do our calculations for our stress. Now, one thing that does arise as a result yeah, so here's kind of the stress distribution that we get for one of those effects about the z-axis and one of those effects about the y-axis, and we just need to add those two things together in order to get our actual situation here. So what you're going to end up having happen there is you're going to end up having, you know, a certain maximum stress and a certain minimum stress, kind of based, and it'll be different. You know, there's 4 corners that are possible candidates for where the maximum stress could occur, and it's kind of it depends upon the combination of whether or not this moment about here is positive or negative, and this moment about here is positive or negative. This is determine kind of at which corner the stress is going to increase, combine constructively to get a maximum, combine destructively to get a minimum, or slightly cancel out in order to get something in the middle at these corners. So we're also going to still get a neutral axis. Unlike the neutral axis for a symmetric bending situation, it's not defined solely based upon the geometry, because basically what we're going to do is we're going to have, you know, this combined with this in a manner that causes those two things to combine together to create zero stress at various points along the cross section. So there's still going to be that line where there's zero stress. So like in this instance, it's right here. But where that line occurs is based upon basically the ratio of the i's. So the I about this axis, so our IZ and our IY, as well as the ratio of the two moments, the moment about this axis and the moment about this axis. So we could define that as the ratio between those two, or if we look, or we could just define that based upon this angle here. So the angle that kind of is being the angle theta there is basically a function of the ratio between the moment about the z-axis and the moment about the y-axis. So if we want to figure out where the where the neutral axis occurs relative to here we're working relative to the z-axis, and we just need to use this formula here, where the iz the this angle alpha here, where the neutral axis occurs relative to the z-axis, is based upon the ratio of the iz to the iy and the tangent of the theta here, the tangent of the what am I trying to say here? The tangent of the angle between the moment that's actually being applied and the z-axis as well. And that's basically us. That can be found basically by taking this formula here and solving for the points where sigma is 0. The next part to talk about is composite beams. So previously we've been kind of working upon the assumption that the beams that we're looking at, they're all made of the same material. If that is not the case, then the assumption that our stress varies linearly from the neutral axis is not valid anymore. However, our geometry dictates that the strain still varies in such a fashion. So the stress is going to be proportional to the strain times the Young's modulus for the material that we're looking for. So we need to be able to figure out essentially how the fact we're using different materials affects both the the location of the neutral axis and affects the stress levels. So yeah, here's an example of one way we could do things. We could bind some steel plates to some wood in order to increase the bending resistance. So this example here, we've got these two materials here. We've got a stiffer material on the top, and we have a less stiff material on the bottom. And it's going to result in, again, we still have a linear strain variation. So the strain is going to vary based upon the location, how far up and down the place we're looking at is from the neutral axis. Of course, we don't yet know where the neutral axis is, but we'll get to that. And that's going to result in stress variations, because we basically need to take this strain variation and multiply it by the Young's modulus for the two materials in order to get our stress variation. So when we get to the less stiff material, the stress level drops down. Now the way we go about to figure how this works is basically if the less stiff material is going to be carrying less of a load than the stiffer material of an equivalent size. Or the other way around, a less wide portion of the stiff material can carry the same load as a wide portion of the less stiff material. So what we do is basically we kind of take the composite beam that we have and we transform it into a beam of a single material by taking the two materials and increasing or decreasing their width Now, only the width, not the height. We increase the width, well, increase or decrease the width. So if we're going to transform it into the less stiff material, then we need to take the stiffer material and increase its apparent width. Or if we work the other way around, if we're starting with if we're trying to transform everything into the stiffer material, then we need to take the less stiff material and decrease its apparent width. So we use these stiffness ratios to do that. So we got this relationship here. B2 is equal to NB. So B here was the original width of the material being transformed, and N is just the ratio of the Young's moduli. So the nomenclature that the textbook uses is that they use N for a ratio of E stiff divided by E. What's a good word for less stiff? Floppy. Whereas, I guess if I'm telling you what the nomenclature is, I should also specify that that was a lowercase n. And then down here, they're using n prime. And that's the ratio of that's just the inverse of that. So either way works. So you just need to take these two materials, transform them to one material, figure out what the cross sections properties are for that. So we got our new cross section here, so we need to find out where the neutral axis would be based upon that geometry. And we need to figure out what the I is based upon that geometry. So here's just another looking at another way. So like if we have wood and steel and we want to transform this into all steel, we do that by essentially making a steel T-bar by multiplying the width of that wood by the ratio of the stiffness of the wood divided by the stiffness of the steel. So here we're starting out with 150 millimeters for the beam, but the wood section gets transformed into an equivalent 9 millimeters width of steel. And then we calculate the location of the neutral axis, and we figure out what the I is for that. And then from that, we find our stress distribution using our flexure formula for the new fake all steel beam. So this one would have, it would end up having when this moment is applied, it would end up having a maximum stress down here of 7.78 megapascals, and it would end up having a compressive stress at the top of negative 28.7 MPa. That would be what the stress distribution would be if this was actually all steel. But when we go back to the actual situation, that stress distribution was based upon kind of the strain. So again, our stress is proportional to the strain and the Young's modulus. So when we want to go back to transform it, we take that, 78.6, and then we multiply that 78.6 by, again, the ratio of the stiffnesses, the ratio of the Young's modulus of the wood and divided by the Young's modulus of steel, which reduces our actual stress level in the wood by a significant margin, because wood is a lot less stiff than steel. So as a result, this composite beam here, we end up seeing that the maximum absolute stress is occurring in the steel, whereas the stress level in the wood doesn't get nearly as high, and that's because it's more flexible. And yeah, so we will do some examples of how to do both those things.